Good afternoon. Good afternoon. My good friend John Shavacco told me that everyone should sit up front. So if you're in the back, please come forward, especially those WaterFurnace people over there to the right. Make sure you move up to the front, please. Come on in. Don't be afraid to scoot up to the front. No Mark. We're missing Mark. You need another chair? Good afternoon. Good afternoon. My name's Ryan Johnson. I'm with WaterFurnace. I run the residential business for WaterFurnace. And, you know, I'm really excited to be here. This is my first NY-GEO. And NY-GEO is really, from what I understand, a pinnacle of the industry. And, you know, one of the things that WaterFurnace and GEOSTAR has done with NY-GEO is sponsored the top jobs. And that's why I'm here today to help with the top jobs projects and presentations. And I'm really excited about it because what it does is it highlights some of the premier jobs that have happened in the industry, and it really gives people an idea to see what other folks are doing. So I'm honored here today to be able to introduce Tony, who won this award last year. So without further ado, I'm going to introduce Tony Amos, and he's going to kick this panel off. Thank you very much.
Okay, thanks Ryan. Yeah, we won it in 2024 actually, so not last year but the year before here. Yeah, what does it mean to me? It's quite a prestigious award. So we're going to be walking through 4 awards: commercial, industrial, new construction, commercial, industrial, retrofit, campuses, thermal energy networks, and then residential. So we're going to bring those guys up in a short while. But I just wanted to give you a quick update. We won the award in 2024. So I hope you guys that are going to collect today's award realize what this is, how it's going to change your lives, because it's really changed mine. I can't go out on the streets now without dark glasses. And it's kind of, so yeah. So Endurant Energy won the project for an energy pile project. So my message has always been explore all the options from a geothermal point of view. Don't just think geothermal is all about drilling boreholes. There are a multitude of other solutions, and this is a classic example of this project. This project's been delivering 50% of the building's heating and about 40% of the building's cooling from geothermal loops that were put into the caissons, 63 caissons that actually support the building. So you can see the award there. It's now on pride of place in our entrance lobby, and you can see us there collecting the award with John Thomas from WaterFurnace. Just a quick update. One of the coldest days of the year. This year, we were told it was the coldest in like almost 100 years. And what we can see here is we're delivering in that peak period water at about 45 degrees to the heat pumps on the roof of this building. So, and the way that we're managing this particular project is we're treating the ground underneath this building and the foundations like a thermal battery. So in the summertime, we're trying to drive the ground temperature up to about 90 degrees by dumping as much heat into the ground from the cooling process, so that by the time we get to the winter time, you know, we've got a very warm ground and potentially we can deliver even more heating and importantly, as energy efficiently to the heat pumps as possible. So this little table here shows you some of the efficiencies that we saw at that particular moment on the coldest day. The ground source heat pumps here We're delivering, the temperature coming out of the ground was 55 degrees Fahrenheit, outside air temperature 13. COPs of about 5.7 from the ground source heat pump and an air source heat pump, but those temperatures would have been delivering heating with a COP of 2. So again, back to Donovan's message this morning, you can quite clearly see here how using ground source heat pumps in these coldest times of the year compared to air source heat pumps. There's a lot of ground source heat pumps will deliver 2, if not 3 times the levels of efficiency. So that's just an update from the award. Project's running really smoothly. Anybody want to go and see it, give me a shout out, and we're happy to take them down there. And now for the 2026 awards. Should have a bit of a drum roll here. So this is what I feel is like the geothermal Oscars, basically. So like I said, guys, it's going to change your lives. So I hope you're prepared. So without further ado, let's move into the first award. So these guys have got 12 minutes each, and we're going to have questions at the end. So there'll be a roving mic too. So Justin, do you want to come up and provide your presentation?
Will.
I'm going to be timing you. Thanks.
So since this is the geothermal Oscars, is there going to be like exit music to get me out of here, or? Okay, so our submission this year was Creekview Apartments, Phase 2. This is a project, it was a multifamily low-income housing project in Canandaigua, New York, just outside of Rochester. It was a new construction project, and there's a lot of really cool stuff going on here. All of these structures were built to passive house standards. It's a near net zero project utilizing geothermal for heating, cooling, and domestic hot water, as well as a centralized ERV system. This project being a low income, it was subsidized by several different organizations here in New York, NYSERDA being one of them. There was low income tax credits available, and so this kind of hit all the hot button topics for multifamily. So it's a total of 72 apartments within these structures. We have a total of 21 variable speed water-to-water heat pumps. And like I said, we're doing 100% of the heating, cooling, and domestic hot water in these spaces. It's all vertical bore fields. The refrigerant impact minimized to the space. In phase 1, they did all mini split air source heat pumps. And so it was a pretty big upgrade to go all ground source for phase 2. So not only aesthetically is it much nicer looking, but it's also quite a bit more efficient. So this is, kind of some overviews of what the mechanical rooms look like. These are split up into a few different layouts and designs depending on the building and the square footage of each building. There's either 2 variable speed water-to-water units or 3 in each mechanical room. Each mechanical room has 220-gallon indirect water heaters, and like I said, we're providing, to every unit within that building. The mechanical rooms, because of our no buffer tank design direct to load, makes the mechanical rooms quite small. So this is some pretty good implementation and letting technology work for you with a true variable output hydronic system. The mechanical room layouts here are kind of strange, so the ERVs kind of sit up in this vertical hole. It's kind of hard to take pictures of that, but it's all Renew Air ERV systems in this building. The contractor in this particular case was VanHee Mechanical. They did a fantastic job, and hats off to them for doing really stellar work. And this is, all around, it's a pretty interesting project. We got variable speed pumping on the source side. All the units pull from the same source. And so, in a lot of ways here, we've got a lot of technology going. These units are all Wi-Fi connected with onboard energy monitoring. We can look at anywhere, I think it's about 219 data points that update to the cloud every 3 seconds. All of that's remote available. We can make settings changes remotely. So there's a lot of tech going on inside this structure here. There was a lot of, like I said, tax credits and financing help with this project. NYSERDA Building of Excellence stepped up, and then early design support. There was just a lot of involvement from a lot of different players to bring this to reality, and people have, I don't know if every apartment is full at this point. I was there about a month and a half or 2 months ago, and there was a lot of people moving in. All the buildings are up and fully functional at this point. Some of the obstacles that they overcame on this project was, being able to do all of this with the electrified network, no fossil fuels, and doing a mechanical system redesign that really worked for the application as well as the technology and mechanical systems that went into the building. Having centralized hydronic heat pumps that are direct to load, feeding multiple different apartments and different zones. Although it kind of looks clean and simple in the mechanical room, there is a lot to deal with there. And it's working really well. And like I said, the alternative here was doing air source mini split type systems. So that's what they did in phase 1. And so, phase 2 is a pretty significant upgrade. So some of the players here from the development and owner and this Baldwin Real Estate Development, DeMarco Contractors was the GC on the project. VanHee, like I mentioned before, was the mechanical contractor, and SWBR was the architects. And yeah, we've had a long list of people that contributed to this project. This has been ongoing quite a while. The first time I actually found out about this project was at NY-GEO, I think 2 or 3 years ago, and sat in the side room and kind of started making the preliminary designs for this at that time. So it took a couple years to bring it to reality, but here we are. All right, well, I'll pass this off to who's next. Matthew? Oh, I'm sorry, is that you?
That's me.
Okay.
Good morning. My name is Mark Preston, Project Manager with Adams European Contracting. Today I'll be presenting our geothermal domestic hot water system retrofit at New York City's Housing Authority, Eastchester Garden and Jackson Houses complex in the Bronx. This project represents a major step forward in decarbonization of domestic hot water systems in large multifamily buildings. Domestic hot water in multifamily housing has been a persistent challenge. Most systems are aging and inefficient, with high carbon emissions from conventional fuel sources. At the same time, energy costs are rising, and we're seeing increasing constraints on the electrical grid. There has not been a scalable, reliable solution for decarbonization of domestic hot water systems until now. Applying geothermal to domestic hot water at a scale is not straightforward. You're dealing with continuous demand, high temperature requirements, and variable loads. Efficiency often drops during peak demand, and systems must integrate into existing infrastructure, which adds complexity. This is not a plug-and-play solution. It requires innovation. NYCHA set a clear objective: 40% reduction in energy use and emissions. Develop a scalable, long-term solution, minimize grid impact, and maintain reliability. We developed a fully geothermal domestic hot water system. This includes a borehole loop field, high-efficiency heat pumps, and integrated storage. This was delivered through a design-build approach, allowing innovation without constraint. See the following video.
Best Residential Hospitality, and Best Project Excellence in Sustainability. NY-GEO, Eastchester and Jackson Houses, Geothermal DHW and Heating Upgrade. A pioneering geothermal system was introduced to replace fossil fuel hot water infrastructure across multiple residential buildings setting a new benchmark for sustainable urban housing. Closed-loop vertical heat pumps now provide year-round hot water, improving efficiency while eliminating direct emissions. Developed in partnership with a manufacturer, the dual compressor system delivers reliable high-temperature output at double the performance of typical systems. Advanced features include liquid injection technology, double-walled heat exchangers, efficient storage tanks, and instant response mixing valves that meet health and safety standards. These improvements reduce water waste while safeguarding residents from risks associated with traditional systems. Work in occupied buildings demanded a phased approach to minimize disruption, with strict attention to site accessibility. Utility approvals were secured through early engagement and dedicated coordination. Leaks in aging infrastructure were resolved with rapid inspections and repairs, supported by advanced leak detection tools. The system improves resilience against fuel price volatility, reduces emissions, and provides tenants with efficient, reliable hot water, demonstrating how sustainable technologies can be applied at scale in dense multifamily housing.
At Jackson Building 7, we installed 10 boreholes, each at a depth of 500 feet, with a minimum spacing of 30 feet apart. This configuration was replicated across all 7 buildings in the development. This allowed us to scale efficiently while maintaining performance. We infused the loop field system with a methanol solution to stabilize the loop field during the winter months. Due to spacing, we had several types of drill rigs. For the areas between the playgrounds and the building, which was the shortest, we had a smaller rig. We used an instantaneous geothermal heat pump system to produce approximately 140-degree water from an incoming temperature of approximately 45 degrees. Energy is continuously extracted and transferred through heat pumps. The system uses a combined storage strategy to maintain efficiency under varying demands. Therefore, the system is optimized for real-world demand variability. This is an overall schematic of our system, where we had the ground source loop field come into the manifold through the pump system and then back down. Then we had the incoming water go through the heat pumps, either to the mixing valve and straight up to the building, or to the storage tanks, depending on demand. This is a 24-hour runtime of our heat pumps during the demand peak. Here's operating temperatures over a 24-hour period. We would constantly produce the 140-degree hot water and send it up to the building at 120 degrees. Through the design process, we started off with a 0.8 COP of the existing system. Then the contract was to provide a 1.0 COP of electric. The 30% design was intended for a Colmac, which we were going to get a 1.8 COP. Then we introduced the WaterFurnace unit under a high flow, and we got a 2.2 COP. Then through controls and low flow, we started achieving a 3.42 COP. And even further with the low flow and further advanced in controls, we ended up achieving a 4.55 COP. The results are significant. Capacity increased by 63%, heat extraction increased by 231%, efficiency improved by 153%, and power consumption decreased by 21%. We are delivering more output with less energy. The system operated at approximately 43% capacity while still delivering consistent 140-degree temperature. This demonstrates strong efficiency, margin, and reliability. The system exceeded design expectations in both efficiency and output. Therefore, we had the performance independently verified by NYSERDA. The project introduced several key innovations: 100% geothermal energy for domestic hot water year-round, cold water storage for peak efficiency, serial storage design using shared piping, and 180-degree output using standard heat pumps. These solve the biggest barriers in geothermal domestic hot water systems. These innovations eliminate fossil fuel dependency, they maintain efficiency under variable loads, and they improve reliability, lifespan, and overall system performance. The system achieved a 40% reduction in carbon emissions. It operates entirely on geothermal energy and significantly reduced overall energy consumption. The system reduced peak load in demand and lowered total power consumption by 21%. This may eliminate the need for grid infrastructure upgrades. It supports electrification without adding grid strain and overloading the grid. The design-build approach was critical. It allowed full integration of engineering and construction and enabled rapid innovation in custom control system development. This system is highly scalable. It can be expanded to include heating and cooling and replicated across NY-GEO and other multifamily buildings. The Lou Field has a lifespan exceeding 200 years. The equipment lifespan is approximately 30 years. Maintenance is low, and life cycle cost is highly favorable. This is one of the first 100% geothermal domestic hot water systems of its kind. It delivers high performance with lower energy use. It reduces grid strain, and it's scalable and cost effective. This system demonstrates that geothermal can fully replace traditional domestic hot water systems in large multifamily buildings. We're not just reducing emissions, we're improving performance, lowering energy use, and reducing grid strain at the same time. This is not a concept, it's operating today, and it's scalable for the future. Thank you.
How are we doing, everyone? I'm Matt Damaris from Energy Catalyst. I'm going to be talking about the Hawthorne Valley Waldorf School. It's a very unique project in upstate New York. It's a Waldorf school, so there's no square rooms anywhere in it. It's all octagons and triangles. Very, very difficult building to retrofit. And there's actually, one piece of clarification, there's 5 total buildings here. 2 of them are attached to each other, so. But this project had a lot of the classic constraints that you see in a lot of geothermal projects. All they had in any of the buildings was old baseboard, 180-degree baseline design, very little space to add ductwork. They didn't really have any options for rooftop units or any other types of systems that might have helped. And one interesting little constraint that they had is they had a very limited power budget. So they had about 600 amps total coming into their building, and basically they were using about 250 amps in total. So our solution ended up adding about 250 amps, so they still had a 100 amp buffer, which was pretty good, and that's our max capacity, so we weren't ever really going to exceed that. But the air source option would have required them to upgrade their electric utility, and that by itself would have been several hundred thousand dollars, but also really changes the entire scale of the project. It changes it. But one of the biggest constraints that they had was also just that they had a very small budget, $2 million for 5 buildings, about 45,000 square feet. So really, really tight budget. And for most of you engineers that are in the crowd, you would probably guess right off the bat that this project could easily die in the vine. It's not necessarily an easy project to do. And that's exactly the type of project that we love taking on. So what we did is we looked at the project and we figured out right from the beginning, if we converted the entire system to forced air, we would need 1,600 CFM, and we only had room to put 5,000 CFM. We're talking specifically about the main building here. So we had to find another way, and what we ended up doing was reusing all of their existing hot water baseboard, and we used 5 8-ton double hybrid heat pumps, which we manufacture in Troy, New York. And we reused all the existing baseboard. So these units can operate in hybrid mode. It's a proprietary mode that we created. And basically what that does, it delivers about 80% of its energy as high efficiency hot water, and then 20% as hot air. And I'm gonna get into the details of why that's valuable in a second. And then all the units are connected through a central buffer tank, and they'll all operate as a coordinated system. So even though there's 5 individual heat pumps spread throughout the building, they all operate as a central plant in reverse. So let's talk about that refrigeration cycle and its advantages. So in a regular compressor, you would have your gas coming out of the compressor. It condenses across the heat exchanger, makes your hot water. And you may have, say, 120-degree liquid refrigerant coming out of there and heading towards the expansion valve. And if you were to look in that pipe, what you would see is that in that pipe is 120-degree liquid, right? It's phase change, it's giving off its energy, but you still have 120-degree liquid. And across the expansion valve, you have this very, very low temperature. Well, for the engineers in the crowd, where's that energy going? Where's that 120 degrees going? It doesn't disappear, it's conserved. Energy cannot be created or destroyed. So when it goes across the expansion valve, it robs you of your efficiency. It's one of the number one reasons why, as you get to higher and higher temperatures on a heat pump, that you get lower and lower efficiency, because there's more residual energy left over. So what we did is we thought, well, we need to supplement the hot water baseboard anyway, so why not put an air coil into our unit, and we can deliver about 90 degree to up to about 110, depends, but we can recapture some of that energy, and then the hot air that's delivered out of the unit can come and serve the building to help heat it, but it's also a byproduct of the refrigeration cycle itself and can substantially improve the efficiency, up to about 30%. So this project also really challenged us. So we had been using that refrigeration cycle for a long time, but we also saw the opportunity to improve the way that we attack these projects, right? In general, it's not very difficult to get the whole mass of a building, using low temperature baseboard, to whatever temperature you're trying to get to, 70 degrees, right? It's not very hard to do that. What is very difficult, though, is to accurately predict in advance which handful of rooms are going to be cold, which one has the bad windows, which one has a corner room, which one has undersized baseboard or blocked baseboard, right? You're working with an existing infrastructure on this building that was over 100 years old, and so it's extremely difficult to project and predict ahead of time what that's going to, where you're going to need supplemental heat. And that's where upgrading our controls into essentially a full integrated BMS allowed us to really solve that problem. So now every single one of the heat pumps within the buildings, they would coordinate with each other automatically, and they would make real-time adjustments to the hot water temperature going throughout the entire hot water loop based on thermostat feedback. They would support each other, so if one went down or if one needed more load, the other one, even if it doesn't have demand, will turn on and start supporting. And then we also have remote optimization. So a lot of companies these days have remote controls and remote data collection. Ours is actively using we're actively optimizing the system remotely. So the result is that we have a decentralized system that becomes like a single intelligent unit. So a couple of photos here. Everyone loves to see the photos of the construction. So on the bore field side, we use 17 500-foot twisters, and we also use a combination of both vertical and horizontal drilling. So here's the horizontals, and it allowed us to duck under a lot of objects that were in our way, such as roads and playgrounds. Here's some installation photos of the twisters. The twisters work extremely well. We've been a huge fan of them for a long time, and you can kind of see the row of them as they're being built here. And then just a couple of other photos here. We are setting a twister down the hole, and then we flush the system out with our own flush truck. So the main building, we built a lot of resiliency right into the whole system. So on the main building, they used 10 of the 17 twisters. And what we did is we put them in 5 sets of 2. So that way, in the worst case scenario, if any one set of them went down, say in the middle of winter where it couldn't be repaired, then we still have 80% redundancy. We can isolate that individual set, and the system can still chug along. So a couple other photos here. You can see during construction, we had to hide all the ductwork, so we tore down a fair amount of the ceiling and hid all the ducts up in there. And we learned a couple of really interesting lessons along the way. I think I know it's a little small, but if you look at this graph here, this is the twister performance over time. And this is during a negative 15-degree weather event. We had obviously, as everyone knows, we had a really cold winter this past winter. And you can see, even during this period of time, the twisters held up extremely well. They're 125 feet per ton on this project, and basically never got below 40 degrees at any point. Here's those same twister loops over the coldest 2-week period of the winter. And again, you can see they did get down almost to about 41 degrees entering water temp, and then they kind of bump back up, and they're sticking around 43 to 44 degrees. In terms of efficiency, the approach that the hybrid approach certainly did allow us to get better efficiency. But in addition, it also allowed us to use lower temperature hot water on the shoulder season. So this data here, where you can see about a COP of about 4 to 4.5, this was during some of the coldest weeks of the year, the coldest 2 weeks. But definitely you can gain a lot of efficiency on your shoulder months. Like technically today's still a heating day, and we can probably be supplying maybe 100 to 110 degrees on a day like today. Yeah, so one of the biggest takeaways, and for a lot of engineers out there who might be facing projects like this where you're trying to figure out how do I retrofit existing buildings with hot water baseboard or radiators, the thing we really learned is that a little bit of air can go a long way. So like I said, if you have that pesky room, if you have spaces that potentially are going to be hard to heat, by supplying and circulating a little bit of air, number one is you can actually level out the temperature, so your rooms that tend to be a little hot can actually be cooled down. You can share some of that hot air and put it over into the rooms that need it. And then we also leveraged it for all kinds of other things. The building didn't have any central air or cooling, so now they do, which is a law in New York State as of, I believe, last October. So they now have cooling in every single classroom, which is a big advantage. And then, like I said, the air allows us to operate at lower overall hot water temperatures for the building, which is a big improvement. And this project on average is expected to get about a COP of, seasonal average, about a 4.5 to 5 COP. So just to finish, there's often this mantra of, it's very difficult to retrofit buildings with existing hot water, kind of the unloved projects that we typically see. But I think we've proven here that it is definitely possible to electrify these types of buildings, and that the high temperature, if you have existing high temperature hydronic systems, that is not necessarily the barrier that it once was. And then we do highly advocate for the decentralized systems versus the centralized systems, just because you can deliver your energy much closer to where it's actually being used, and then you have the built-in redundancy right there. So if one unit goes down, you always have that redundancy. I'm just going to end with a quick quote here for those. You can probably read it, but I can see that I got 30 seconds left on my clock, so I'll read it for you anyway. But this is a statement from the director of Hawthorne Valley School. He says that it's no small feat that we were able to complete a massively complex undertaking in 5 buildings. Some of them are 200 years old and on budget. It is heartening to come to school on days when the temperature is below 0, see no smoke coming out of any chimney, and walk into warm and welcoming spaces. And just a little bit, a comment on that. We took out all the boilers. There's no backup heat in this building. A little bit of electric resistance, but it was a full send. So, yeah, thank you very much, and appreciate your time. I'll let the next person.
Hello, I'm Jeff Hoffer with Aztec Geothermal. Glad to be presenting our residential system. Just a little bit about Aztec if you're not familiar. If you want to find out more, we have a booth outside. This is our project. Project name is Bonnie View. It's in Lake George, New York, which is about an hour north of Albany. And it's okay, why is our slide moving here? This is an auto. Just make sure it stops.
Want to get out of here?
No, it looks like it's staying there now. Okay, I might have been hitting it with my, oh, no, it's not. Get out out of this and change the operation. Get rid of use timings. Okay, as I was saying, this is in Lake George, New York, about an hour north of Albany. Beautiful big lake. It's about 45 minutes north of our shop. The team we were working with, the architect, the builder, so Balzer Tuck and Teakwood and Aztec Geothermal. This is our fourth project that we've worked on together. And they involve us early in the design process. We met with the homeowner, we met with the architects, we met with the builder, incorporated a lot of designs that we had done with previous homes with this group. We also enlisted a mechanical contractor, did all the radiant floors, did all the duct work. Our drilling contractor was Rosick Well Drilling, and we also incorporated the home automation contractor as well because we had a lot of connected systems and used the home automation that they put in for the homeowner. The specs on the home is 8,000 square foot house, super energy efficient, spray foam insulation, triple pane windows. We ended up going with a 8-zone system, which incorporated both radiant floors for heating and air system for heating and cooling. These are the components of the HVAC system. The heart of the system you can see in the photo there. 3 4-ton water furnace, NSW, water-to-water heat pumps. We went with 4 450-foot vertical ground loops, incorporated 6 First Company hydronic air handlers for heating and air conditioning. Used warm board for radiant floors on the first floor, and the basement we had radiant in the slab. Incorporated simultaneous heating and cooling. I'll get into that a little bit down the road. Used TurboMax buffer tanks, Savant thermostats, Honeywell zone controls, HBX set point controllers, and you can see the rest of the components there. Some of the systems that we incorporate into it, number one was simultaneous heating and cooling. I got a little bit of our piping diagram there that shows how we're incorporating circulators and valves to switch between. We ended up with 2 buffer tanks for heating and 1 buffer tank for cooling. And pretty much throughout the year, I'm maintaining temperature in the hot tank as well as the cold tank for different needs in the house. Now, the benefits for simultaneous heating and cooling in a house like this, there are certain functions year-round that might need cooling or heating. A good example in this house, they have a golf simulator room. So February, they might get a little, and it's in the basement, so there's not a whole lot of loss in that room. So they may be running the air conditioning in February there. In the summer, I've seen houses like this where they'll run the radiant floors in the basement because they'll just get too cold in the summer while the air conditioning's on. So it just gives them the ability to do that. I'll also go over some other functions that use the cooling and the cold tank year-round. And for anybody who's ever done a hydronic system, it starts to get complicated in a house, and it can be a real challenge with the homeowner to get them to understand, well, it's now June, so the system needs to be all cooling for everything. And okay, now it's October, so now I need to switch everything, and everything is heating. It's so much easier that they just do whatever they want on any thermostat, and they get whatever they need, and there's no questions of, what time of year is it, and can I do this, and I can't do that. So. And then something else I incorporated, it's the first time I tried this. I'm pretty happy with the result. We used the TurboMax buffer tank that will also use some products specifically for domestic hot water production, but in this case I incorporated it into my hot buffer tanks, so we're just feeding the cold water through the TurboMax internal heat exchanger and then supplying that to our boilers that do the finish domestic hot water, but it's every time it goes through there, preheats it from anywhere from 50 coming in to 95 to 110, 120 in the dead of the winter, just kind of as an automatic process going through that buffer tank. The hydronic air handlers have a couple of functions. I always like to incorporate them in a hydronic system. They're primarily there for cooling, but I like to use them for heating as well. The two functions where it's beneficial to use them is heating, even though first stage heating is radiant floors, but it's good to use that as second stage heating. Believe it or not, 8,000 square foot house, lake home. This is a kind of a summer weekend house. So they'll turn the house down if they aren't there. When the house is trying to recover from 60, it can stage up into that air handler, use the radiant floors and the air handler to bring the temperature up. The air handler also is a backup. Let's say you lose a circulator for radiant floors, you have another source of heat for that space. So. Another thing I like to incorporate, and we've done this on multiple jobs with this builder and architect, is always try and sync my zones up so that you have the radiant and the air handler all controlled off of one thermostat. Nothing that drives me nuts when you go into somebody's house and they have two thermostats sitting next to each other, one's for heating, one's for cooling, or they have thermostats all over the place and the homeowner's confused, they don't understand which one am I supposed to use for this, which one am I supposed to use for this. So one thermostat, one zone does all your control, whether it's heating or cooling. And then another feature, we kind of threw this in during the process. The builder who had worked with this homeowner on a previous job, the homeowner's biggest pet peeve was that their mechanical room was too hot in the house, and they were constantly complaining about how hot the mechanical room is whenever they went in there. So we added in a multi-aqua hydronic fan coil unit in the mechanical room, only runs cooling, and it pretty much runs year-round, and it's just cooling off that space. So it's in the dead of the winter, we do have boilers running, all the pipes are insulated, but you still have a lot of heat in that room, and it's buried in a basement, so there's no real loss there. So just a creature comfort for the customers, and the builder was ecstatic about it because they were tired of hearing about this other house that always has this hot mechanical room, so easy fix. And once again, a reason for simultaneous heating and cooling, because even in January, this unit in the house is running cooling, so it needs that cold buffer tank, the chilled water in it. Some of the other integrated systems we added, they have a wine room. This is a wine guardian. We found a water-cooled wine guardian, so that's linked to the geothermal system. Once again, we're using the water out of the cold buffer tank to do the cooling for the wine guardian space conditioning. We are using Fantech ERV. We have one centralized Fantech ERV. It's doubling as bath exhaust and ventilation for the house. So we're pulling all the exhaust out of the bathrooms. We have timers built into the bathrooms that the homeowners can select, ramp up the ERV to a high speed if they're using the bathrooms, but otherwise that's where we're pulling all the air. And then the fresh air is distributed throughout the house using the air handlers. And then we also incorporated at the house, they have an outdoor spa. Most of the time it's covered up and not being used. In those instances, we're heating that spa with the geothermal system. When they're using the spa and it's February and it's 10 degrees outside and they want the spa to be 105 degrees, a little bit of struggle for the geothermal, so we flip over and let them use the boiler during that period of time, but 95% of the time the geothermal is keeping that spa from freezing up in the winter. I throw this up there. This is our wiring diagram for one of the mechanical rooms. There's two mechanical rooms in the house, and you can only imagine the amount of wire that runs between the two of them. So, and my heading on this is simplistic controls. When you first look at that doesn't look very simplistic, but a key design feature that I try and factor in is I use all off-the-shelf components. So TACO, zone control relays, HBX controls, things that if I'm not around, somebody can find a manual online, somebody can call a resource and have things that people are familiar with. Pretty much every HVAC contractor knows what a TACO relay panel is. Label everything so that people know, if this light's on, what does that mean? But just try and make it's at heart a complicated system, but it's also basically a bunch of little systems all linked together with basic components, so most HVAC technicians can make themselves around it. You also made sure everything possible is connected remotely. So we use HBX set point controllers. I put up a snapshot from my phone. I have access to both of the HBX controllers. I monitor through, this was the first winter it was running. I log in periodically, see how it's running, make some adjustments to the outdoor reset, make sure it's working correctly. It's just nice to have that ability. See if on a really cold day, how's the system performing. Also, the thermostats, home automation, the home automation contract wanted to use Savant thermostats, so we use those. The homeowner has an app that does all their lighting controls, their spa control, their thermostats, and we integrated that into our system. And I also have access to that, so I can see how the house is doing from an individual room thermostat standpoint. And then, of course, since we have the WaterFurnace heat pumps, need to have Symphony monitoring. So we can look at, there's our energy graph for the use, the tail end of last summer once we got the system online and through this winter. So, not only can we monitor the performance, I can see how the ground loop's doing. I log in on a nice cold day or look at historically how it performed during the winter. And then another interesting story, oh, I'm sorry, 2 minutes, okay, I think I should get there. Another interesting story of some of the safeties. I always like to link, especially on a high-end home, I'm concerned about water damage. I always interlock the condensate safeties. If a condensate pump is not working, if we sense water on the floor, we have different sensors, shut the system off, but I always like it to notify us so that we can do something about it rather than find out on 4th of July weekend when the homeowner shows up that they don't have any air conditioning. So how do you get notified? And in this case, I set it all up with just closures on relays and then talk to the safety alarm contractor, hey, can I get these out? And then they inform me at the last minute that, sorry, we've run out of spots on our system, so we can't use can't add your alerts to it. So I just added them into the Symphony has a home automation function. I was able to add that into Symphony. We and the homeowner get a notification if any of those safeties are activated. Some of the aesthetic design, these are all the thermostats, 8 zones. All the thermostats are on one wall right in the mechanical room. We have sensors out in all the rooms, so the homeowners don't have to worry about looking at thermostats, and they can control it manually from the mechanical room or from their app. They love the linear mud-in wall grills for a style. The other thing we've incorporated, and we've done this multiple times with this builder and this architect, these linear floor grills, you'll see them in these pictures, and they'll end up running the whole length of a wall underneath the glass, but then there's only certain spots, they're actual airflow, but they love the look of that design with this type of house. And then most importantly, I was doing the walkthrough with the homeowner, and what I was told by the wife was they had been living there for a couple of weekends, and she let me know that the system is so amazing, it's so quiet, it's so comfortable, I feel like I'm living in a hotel. And I felt like, okay, our mission was accomplished. And I throw this out, we talk at a conference like this constantly about energy efficiency and renewable energy and reducing carbon footprint, but after doing this for 18 years, I can pretty much say from a residential standpoint, the #1 comment I get from customers when the system is all said and done, they don't tell me about how much they're saving, they don't tell me about it's wonderful that the oil tank is gone, they always tell me how comfortable the house is. It's always exactly where I want it, every place in the house feels exactly the same. That's what they love most about the system, is how comfortable it is. Thank you.
Okay, thank you guys. Very, very worthy winners. I'd just like to say, Jeff, I've got a house very much like that, and it's incredibly comfortable, but I don't have a wine cooler chiller. I need to get one of those. You need to give me the details of that. Before we go to questions, I'd just like to thank all our judges. Personally, I don't know who they are, so we can't bribe them in any way, but I'm sure they know who they are. So massive thanks to those guys and girls. And I'd just like to mention Joanne Coons, who would normally moderate this session. Unfortunately, she couldn't make it today because her husband's not very well, so send her and her husband best wishes on that. So I've got loads of questions, but I'm not allowed to ask any questions unless, so let's open the floor to any questions. Anybody want to start? If not,
hello, my name is Alicia Jenkins, I work for Sierra Club, Connecticut. Thank you all for your panel. This question, or questions, or maybe quick, goes to the project in the Bronx. Okay. So, why hasn't there been a full geothermal or tenants heating, cooling, and heating of water for those buildings? Or why is it only heating water? And is gas still being used to heat the houses and cool the houses? And why only domestic hot water? I know it's not a question.
It's okay. It was part of the budget. It's budget driven. Yes, the heating right now is still being driven by gas boilers. That was the other part of the contract. First, they wanted to see a domestic hot water system before they ventured off into the next phase.
question on the back. So just as John Givaco said, tell us who you are, company you work for, before you ask the question.
Thank you guys for your panel. Question on costs.
Sorry, what's your name and company?
From Pratt Institute of Brooklyn.
Great stuff, thanks.
Costs. So for the NY-GEO housing, how do you, like, so when we do cost price, not usually $100 per square foot, right? And the guy who talked about the wall, Mr. Blue Shirt, right? I'm sorry. So
Matt.
you gave us kind of some costs. So when you talk about the hot water, what are the metrics you use for how much does it cost? Because I looked at a couple of these domestic hot water conversions, and they're pretty pricey. So what's your metric on the cost?
So with our project, the domestic hot water was probably about 40% of the cost of the whole project. And we were able to, again, we itemized it comparing to what we had to do out in the field. But overall, it was pretty much 40% of our project budget.
All right, but so let's say pre-project, post-project, is there like $1 per gallon or some metric like that what is the industry using?
I don't have that right now.
Okay. All right, great, thank you.
Any other questions?
So let's do other costs. So for the house, how do you, if you had to sell your house not on comfort, on cost, what would you I want the cheapest Adirondack house that I can have versus your house. What's the price differential?
That's a good question. and always totally variable. And in this case, I mean, this house, we basically designed the system and then gave them a price for the system. It was design build. You know, we can't even give them a price till we figure out what we're going to actually put in for the HVAC system. And can't even compare this house to, like you're saying, you know, a more basic house. And honestly, we don't talk in figures like that because every single job is so different that I hate to give somebody an idea of it's going to cost about this much, because then it always comes back later on and somebody says, well, you said it was going to be about this much. Well, it's not, because it's different than what we were talking about. So I unfortunately can't really answer that question.
And did you have any, like the federal tax credit, or what were the tax credits for
This house got the 30% federal tax credit. It was finished last year in 2025. New York State, it also got the $10,000 New York State tax credit, and it got a utility rebate, which I think came in at around $25,000 to $30,000 for the utility rebate. So pretty good incentive package for this house.
Thank you.
Hi, John Paul from WaterFurnace. I've got a question for Jeff. What do you maintain your hot and cold tank temperatures at?
So the cold temperature tank, I do a little bit of a reset, on outdoor reset. I'll let it go in the winter up to around 50 degrees. And then as it gets warmer outside, I'll cycle it down to 42 degrees as the coldest in the summer. The cooling demands that I'm using in the winter don't need it to be super cold, so I come off of that a little bit. The hot buffer tank, I think I cycle between 90 when it's like 60 out, and at 0 I'm hitting 120, outdoor reset. I always do an outdoor reset to maximize the efficiency on the water-to-water heat pumps.
And I just want to answer or address your cost a little bit and explain a little bit more what's going on from your design a little bit for this project as well. So the important thing to understand is that NY-GEO has a mandate involved with Law 97. They have to reduce their emissions by 40% by 2050. This is why one of the specs for this, you can do whatever you want, but it has to be saving us 40% of our site emissions. So, if you touch the hot water, you might have people living in it. These were for 1,700 apartments. You saw 7 buildings here. There was another development in this project, and that was another 10 buildings. So 17 high rises in total, simultaneously doing all the tanks for the buildings. So that was a challenge. Number one. Number two, you have to save the emissions. How do you do that? The only way to do that is to electrify. So there are three choices. Number one, you put electric resistance heat in there, which you now have the cost of upgrading not only all the electric systems in the development, but also you have to deal with the Con Edison and have all your streets ripped up, which happens in one of the developments. They had to do that anyway for this project. Or you put in the air source heat pumps, then the question is when you get 140 degrees out, when you have a snowstorm, and or when you have extremely cold temperatures. Because then the COP, the efficiency and the capacity goes so much down that you won't be able to make our water flow. In this country, we're making about 12,000 gallons per day on average in each one of those buildings. So what do we have left as an option? Forget about cost, but there's nothing else there. But in this moment, to do geothermal. Because everything else would have blown either any kind of budget, because the electrical upgrades have been so expensive to do.
Thanks, Jens. So it is now 12:30. I don't want to stop people from their lunch, but I do want to thank all the presenters today. Fabulous effort. Very worthy winners. The other thing I'd like to say is it's great to see one party designing and building these solutions. When you break these solutions down into different teams, that's when things can go awry. So it's great to see all these solutions coming together. It's great to see some horizontal drilling. There are other solutions. Jeff, one of my questions would have been, and we can talk about this afterwards, why didn't you put a loop in the lake rather than drill boreholes? But that's for another day. But it's 12:30. Lunch is waiting. So thanks everybody. Thanks again. Well done, guys. Well done.
Yeah, I'll have to wear my glasses. All right. I gotta act like I'm talking to people and standing here, doing this. Right on. Perfect. Well, if that works for you, then I'm good with that. We good? Is that what? All right, perfect. Yes, ma'am. Thank you.
So we're going to put our twisters, 8-inch casing, put our twisters, which fits in comfortably into a 6-inch well.